In this video, we're going to learn to find partial and infinite sums of geometric sequences. The sum of the first n terms of a geometric sequence, denoted S sub n and called the nth partial sum, can be found without having to add up all the terms, just like arithmetic sequences. We have a formula. The sum a sub n of the first n terms of a geometric sequence is given by S sub n equals S sub 1 times 1 minus r to the n, all divided by 1 minus r, in which a sub 1 is the first term of the sequence and r is the common ratio where r is not equal to 1. We need three things to be able to find this partial sum. We need the first term, the common ratio, and the number of terms in the partial sum. Let's find the sum of the first 12 terms of the sequence 3, 6, 12, 24, and so on. Well, let's get the three things we need. We need our initial term, a sub 1, that's given to us, it's 3. We need the common ratio. We know to find that, we take the second term and divide it by the first term. Our common ratio is 2. And lastly, we need the number of terms in the partial sum. We're looking to add up the first 12 terms. Let's plug it into our formula. S sub 12 is equal to 3 times 1 minus 2 to the 12th, all that divided by 1 minus 2. Plug that into your calculator. We're going to get that the sum of the first 12 terms of the sequence is 12,285. In our next example, they've given our sum in summation notation. We need to find our first term. We'll plug I equals 1 into the rule of our summation. A sub 1 is going to be equal to 4 times negative 3 to the first. We get a sub 1 to be negative 12. Now we need our common ratio. What's being multiplied over and over and over again in our rule? Well, it would be negative 3 raised to a power, which tells us that's what is being repeatedly multiplied. So r is equal to negative 3. And lastly, we need the number of terms we're trying to add up. Now, that's right on the top of our summation notation, n is equal to 7. S sub 7, plugging into our formula, is going to be negative 12 times 1 minus negative 3 to the 7th, all that divided by 1 minus a negative 3. Plugging our numerator and denominator separately into our calculator, we get negative 26,256 over 4, which then divides nicely. The sum of the first 7 terms of the sequence is negative 6,564. Let's apply this to a real-life situation. A job pays a salary of $24,000 the first year. During the next 19 years, the salary increases by 5% each year. What is the total lifetime salary over the 20-year period? Let's round to the nearest dollar. We need our first term, our common ratio, and the number of years we're adding together. Our first term is our initial salary of $24,000. Our common ratio, well, that's what we're multiplying by. The common ratio is actually 1.05. It's not just the 5%, the 0.05. That would only be the raise amount. We need the new salary amount. So that's the raise amount plus our old salary. That's why our common ratio is 1.05, and then n is equal to 20. Let's plug it in. S sub 20 is equal to 24,000 times 1 minus 1.05 to the 20th, all that divided by 1 minus 1.05. This time I just plugged it all in my calculator at once, and then round to the nearest dollar as the directions asked me to. In 20 years, with that starting salary, getting a 5% raise every year, you're going to end up making $793,583. So far, we've talked about partial sums of geometric sequences. Well, now I want to move into geometric series and the possibility of finding the sum of an infinite geometric series. An infinite sum of the form a sub 1 plus a sub 1 times r plus a sub 1 times r squared, and so on, with first term a sub 1 and common ratio r, is called an infinite geometric series. We know it's geometric because we're multiplying by powers of r over and over again, and it's infinite because, well, we're not stopping. To determine whether an infinite geometric series actually has a sum or not, we have to look at r to the n power as n gets large in our partial sum formula. See, some of the infinite geometric series are going to have sums and some of them are not. So again, let's take a look at this r sub n in our partial sum formula. If that r value is a number between -1 and +1, it's a proper fraction, either positive or negative, then that term is going to approach 0 as n gets large. Anytime you take a proper fraction and raise it to a power, it gets smaller and smaller and smaller. So as n approaches infinity, that's going to become practically 0. And what does that look like if this becomes 0? Well, our sum is going to be a sub 1 times 1 minus 0 over 1 minus r. Right? Well, that's going to give me a sub 1 times 1 over 1 minus r. We end up with the formula a sub 1 over 1 minus r. And that's exactly what we're going to see in the summary box. If the absolute value of your common ratio is less than 1, then the sum of the infinite geometric series exists, and it's given by the formula S equals a sub 1 divided by 1 minus r. If the absolute value of your common ratio is greater than or equal to 1, there is not a sum to the infinite series. See, when your common ratio is 1 or larger and you start raising it to a power, it's just going to get bigger and bigger and bigger and grow without bound. We're never going to be able to add it up to a specific number. So let's find the sum of each infinite geometric series if possible. You want to start by finding r and determine if the infinite sum even exists. If it does, great, we'll plug it into our formula. So let's find the common ratio for our first sequence, 1 plus 1/4 plus 1/6 plus 1/64. We find our common ratio by taking our second term and dividing it by our first term. We get a common ratio of 1/4. Since this is in between -1 and +1, this tells me that my sum exists. Now let's find it. We're going to plug into our formula S equals a sub 1 divided by 1 minus r. We get s equals 1 over 1 minus 1/4. Once we simplify that, we get s to be equal to 4/3. This is another time where math is just amazing to me. I can take an infinite number of numbers, add them together, and end up with exactly 4/3. Amazing. Let's try the next infinite geometric series. We want to start by finding the common ratio. I'm going to take my second term and divide it by my first term. It's going to give me 5/6 times, I'm doing the reciprocal here, 1/5. I get a common ratio of 1/6. That falls in between -1 and +1, so I know that my sum exists. Now we find it by plugging it into our formula. S equals 5 divided by 1 minus 1/6. Simplifying this, we get s to be equal to 6. When I add up that infinite geometric series, I get exactly 6. It's amazing every time to me. Next one, let's see if we can find the sum of the series 2 plus 4 plus 8 plus 16. We start by finding our common ratio. We take our our second term and divide it by our first term. That's going to give us 2. This is greater than 1. Since this here is greater than or equal to 1, that tells me that the sum does not exist. No work to do here because the sum doesn't exist. Our last infinite series is given to us in summation notation. I want to start by looking at my r. When looking at summation notation, r is always the number that's being raised to a power. It's the repeated multiplication. That number for us is -7/10. Since this number is between -1 and +1, I know that the sum exists. And now I want to find it. Well, I also need to be able to plug into my formula, I need my first term. So let's find that first term by plugging 1 into our rule. It's going to be 12 times -7/10 to the 1 minus 1 power. That's going to be an exponent of 0. Anything to the 0 power is 1, giving me that a sub 1 is equal to 12. Now let's plug in. Our infinite sum is equal to 12 divided by 1 minus -7/10. Simplifying this, and I always prefer a fraction because it gives me an exact answer instead of a decimal approximation. This simplifies to be 120 over 17. The sum of that infinite geometric sequence is exactly 120 divided by 17.